Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 5.1, Linear Transformations. In Chapter 5.1, we bring together the varying concepts we have learned about functions, matrices, vector spaces, operations in calculus, and differential operators by focusing on their underlying structures and the concept of a linear transformation. Its importance lies in the fact that in mapping one vector space to another, we preserve the linear structure of the space. To get started, let's look at some definitions. A linear transformation, T, this is the notation that we use to represent a linear transformation, on a vector space V to a vector space W is a function that maps the elements of V into W. So this is the notation T mapping V into W, such that for all the U's and V's in your vector space, and C being any real number, the linear transformation T will preserve scalar multiplication, meaning that if you multiply your vector by a scalar, then apply the transformation, you'll get the same result as if you apply the transformation to your vector and then afterwards multiply by your scalar. T will also preserve vector addition, meaning that if you add two vectors and then apply your transformation afterwards, you'll get the same thing as if you apply your transformation to each vector first and then add the vectors together, or add the results together. In general, if you combine both of these properties together, we can say that the transformation of any linear combination of vectors will be equal to the linear combination of the transformation of those vectors done individually first. In this section of our homework, we're going to be asked to verify many transformations are linear or show that they are not linear by identifying which of these two properties the transformation will fail. The vector space V that we start in is referred to as your domain for T, and W is referred to as your codomain, sometimes called the target. So this graphic shows how you start in your domain T, and then your transformation maps these elements into W. And so typical notation will show is that if you start with some vector little v in your vector space capital V, T will map this over into your codomain W by applying T to the vector V, and what you get back is a little vector W. It's a new vector that's been transformed in your codomain. Now it's important to note that a linear transformation will always associate the zero vector in the domain with the zero vector in your codomain. Meaning that if you start with the zero vector here and you apply your transformation to the zero vector, you will still get the zero vector in your codomain. This is really just a special case of preserving the scalar multiplication property. One more definition. The image, also referred to as the range of a linear transformation is the set of vectors in W to which T maps the vectors in V. If an image is not all the codomain, we would like to be able to describe it. So what we're saying is we're taking all of the vectors in your domain, every single one. You apply T to every single one of these vectors, and it might be that these vectors do not cover all of your codomain. They may only cover a subspace of your codomain. This image will always be a subspace. Of our vector space W. Let's look at a simple example from college algebra that we'll recognize before we move on to new examples that we haven't seen before. Consider the mapping T, mapping real numbers onto real numbers, defined by the transformation T of x is equal to x squared. We want to find the image of T and then show T is linear or find a property that it fails. To start with, let's make a little graphic reminding ourselves what this transformation looks like. So make a XY coordinate system. And recall that T of x equals x squared, or y equals x squared, looks like a parabola facing upward, going through the origin. And so it looks something like this. Now for this transformation, our domain is real numbers. This is your domain. And our codomain is also real numbers. This is our codomain. So notice what our transformation does is it starts by taking an element in your domain, the x values. When we apply T to that x value, it squares the x value. So if this is any particular x1, then this would be x1 squared, where x1 could be a positive number, x1 could be 0, or x1 could be, let's put x2 maybe, x2 could be a negative number. So notice that when we square a number, we always get back a number that's non-negative. The numbers we get back always live on the positive y-axis. This allows me to say that our image of T is the set of y values such that y is always greater than or equal to 0. Notice that the image is not all of your codomain. It's not all real numbers. It's only the positive real numbers, or non-negative real numbers. Okay, so that's the image. Now I want to show that T is linear or find a property that it fails. And the two properties that we need to look at are You scroll back in our notes, the properties of scalar multiplication and vector addition. You need to verify that both of these properties are satisfied or find at least one of the properties that is not satisfied. I like starting with the scalar multiplication property. So let's start there. For the scalar multiplication property, we want to show that t of some scalar times a vector in our domain is equal to a scalar times t of a vector in your domain. Here, let's let A be an element of our domain and C a scalar. Now, since A is an element of your domain, it's also a real number. So let's look at our left side of our equation. For the left side, I want to look at just what does T of Cu look like. So here, T of Cu is going to look like T times a scalar times A, an element in our domain. But what T does to any input is it squares it. So this would be the same as Ca squared, or if you simplify using properties of exponents, C squared A squared. Now let's look at the right side of our equation. And I want to verify that the right-hand side is equal to the left side. So now we're going to look at C times T of some element in our domain. T of A is just going to be A squared. And if we simplify, this will be Ca squared. Here I would like you to notice that the left side and the right side are not equal. Thus, T does not preserve scalar multiplication. And because T did not preserve scalar multiplication, our conclusion, T is not a linear transformation. Remember, you have to satisfy both properties to be a linear transformation, or show that one of the properties is not satisfied. If one of the properties is not satisfied, you're done. The transformation is not a linear transformation. Let's try another example. Consider the mapping T that maps vectors in R3 to R3 defined by this function. Notice that whenever we're talking about a transformation, we always have to be given a function that describes how the transformation is accomplished. We have to be given your domain, what vector space we start in, and we have to be given your codomain, what vector we're landing in. Here now we want to find the image of T and then show that T is linear or find a property that it fails. Let's first find the image of T. To find the image of T, consider that I give you some ordered triple in your domain XYZ. So you'll have some x component, some y component, some z component. So here is your starting element at the ordered triple xyz. And what this linear transformation does is it always makes your z component turn into 0. When you make your z component in 0, it takes your starting vector and projects it down onto the xy plane. If I were to give you a different element in your domain to start with, it would be projected again down into the xy plane. And what you'd like to see if you did this with every ordered triple, well, eventually you'd cover the entire xy plane. This allows us to say that the image of t, now there's a couple ways you can say this. You can say it's the xy plane in R3. It's important that you say R3. It's the xy plane in R3. Or you can write it in set notation as the set x, y, 0 such that x and y are both elements of the real numbers. Important. Do not say the image is R2. And the reasoning here is R2, recall, these are ordered pairs. These always look like x comma y. And what we're given back is not an ordered pair. We're always given back an ordered triple. And an ordered triple is not an ordered pair. This is not an element of R2. It may look like R2 because it consists of the xy plane, but technically there are 3 elements every single time. The value we get back is always going to be x, y. This, the third component, just happens to be 0. But again, you must distinguish that this is R3 and not R2 still. Okay, so now let's show that t is linear or find which property it fails. And again, I generally like showing scalar multiplication first. So here we want to show that t of a scaled version of a vector in our domain is equal to a scaled version of t times a vector in our domain. And I'm going to start with the left-hand side. And let's pick what a vector u might look like in our domain. A vector u would have to consist of 3 components, an ordered triple. So x, y, z. Now, if you're thinking about order of operations, then what we should notice on the left-hand side here is that we have a scaled version of some vector. And remember, when you scale a vector, you distribute the scalar to each component of your vector. So then we'll have t of cx, cy, cz. Now we'll apply the transformation to this ordered triple. And remember, our transformation t always makes your z component turn into 0. So when I apply the transformation, don't write t anymore. Just write what happens after the transformation is applied. Now, we would like to see, is this equal to the right-hand side? So on the right-hand side, we'll have a scaled version of t times some vector in our domain. But again, let's put a typical vector in our domain here. Now we'll apply t to this ordered triple. And remember, what t does is it makes the third component always equal to 0. Now we can distribute our scalar c to each component of our vector. And we'll get cx, cy, and of course c times 0 is just 0. So notice that these two vectors are equal, and we have now verified that t preserves the operation of scalar multiplication. We're looking for equality on both sides. Since t preserves scalar multiplication, now we'll move on to vector addition. Here we want to show that t of the sum of two vectors in our domain is going to equal to the sum of t of each of those vectors. Let's start with just the left-hand side. First, we'll need two elements in our domain. So let's let u be x1, y1, z1. And let's let v, our second vector, be x2, y2, z2. So these are different ordered triples. Here, what we would like to do is first find the sum of the two vectors in the parentheses, what we get before we apply our transformation. Recall that the way you add vectors is you add their corresponding components together. So add your x components, add your y components, add your z components, now we want to apply t to this ordered triple. And remember what t does. It leaves the first two components the same, but the z component, the third component, it makes it 0. Now we want to see, is this going to be equal to the right-hand side if we apply the transformation to each vector individually and then find the sum. So here we'll find t of our starting vector u, which we said was x1, y1, z1. And we'll add that to t of our second vector v, which we said was x2, y2, z2. We'll apply t to each of these vectors, and remember t makes your third component equal to 0. Notice I'm not writing t anymore. Now we can find the sum of our two vectors by adding the corresponding components. Notice that the left-hand side and the right-hand side are equal, And so we have shown that T does preserve vector addition. Since T preserves both scalar multiplication and vector addition, T is a linear transformation. Let's look at another example. Consider the mapping T, mapping again R3 onto R3, defined by the function T of xyz is equal to x, 0, 3x. Here, I want to show that T is linear or find the property that it fails. And I also kind of want to give a graphic of this. So remember, what this transformation is going to do is to take an element in your domain an ordered triple. So an ordered triple will have some x component, some y component. When drawing elements in 3 space, the construction lines help give you location. So here's maybe a starting element in your domain x, y, z. Now what T is going to do this is it's going to map it to the point x, 0, 3x. And because the y component is 0, you know that your point will land in the xz plane. So over here on this left-hand plane over here. But specifically, notice that your x and your z components, your z component is 3 times your x component. So if I were to imagine a point that goes through x and then 3x, your x component would be 1, your z component would be 3, so what I'm trying to give you the visualization of, that's not a very straight line. Let me try that again. This is supposed to be a straight line. That your component xyz gets mapped to the point x0, 3x. It gets shifted to this point, which will always live somewhere in this xz plane. So specifically what I'm trying to give you here is the image. Here the image of T, again, one way to say this is just to be able to describe it's a line in the xz plane through the origin. However, another way to describe this line, for those of you that have taken Calc 3, would be to write this as a vector function. And so you may remember writing vector functions in Calc 3. If you have not taken Calc 3, that's perfectly fine. But this is for those of us that have taken Calc 3. So another way to say this as the image of T, it's the vector function r of T that's equal to T times 1, 0, 3, such that T is an element of the real numbers. Either one of these would be fine. Now I'd like to pause for a moment and give you time to show that t is linear or find it property that it fails. So specifically, I'm asking you to show that it preserves scalar multiplication and vector addition, or show that it fails one of these properties. If you could, pause your video while you work on this. After you're done, come back and we'll see if we agree. I'll see you back in a moment. Okay, welcome back. Let's see how we did. And you may have done this differently than me, but I like showing the property of scalar multiplication first. So here again, we're trying to show, is t times some scaled version of an element in our domain, is this equal to c times t of the same element in our domain? So let's start with grabbing what a vector u in our domain has to look like. And since we're coming from R3, a typical element might look like x, y, z. Again, you probably distributed your scalar into that vector first to get cx, cy, cz. And now we'll apply t to this ordered triple. And remember what t does. T makes the x component stay the same, y component is always 0, z component is 3 times your x component. So this ordered triple will look like cx, 0, and then 3cx. And we would like to verify, is this equal to the right hand side? So first we'll look at c times t of a typical element in your domain. Now we'll apply t to this ordered triple. Of course, when you apply t to that ordered triple, we get back x, 0, 3x. We can distribute our scalar c to get cx, 0, and 3cx. So here we want to notice that yes, the left-hand side and the right-hand side are equal, and this transformation does preserve the operation of scalar multiplication. Okay. Now let's look at vector addition. Again, here we want to show that t of the sum of two vectors in our domain is going to equal to the sum of t of each of those vectors individually, then we add them up. We'll start with the left-hand side. We first need to represent u and v, two typical elements in our domain. I like using x1, y1, and z1 for u, then x2, y2, z2 for the second vector. Now, t does not act on the sum of two vectors. T only acts on a single vector. So we must first add these two vectors together. Again, when adding vectors, you add their corresponding components. So t of x1 plus x2, y1 plus y2, z1 plus z2. Now we'll apply t to this ordered triple. Remember, don't write t. When you apply t, you don't write it anymore. You just do what it does to the triple. The x component stays the same. The y component turns to 0. The z component is really 3 times whatever your x component was. Now, while I could distribute this 3 into the x1, x2, I think it's fine to leave it here for now. And now what we want to do is see if this is going to equal the right-hand side. So first we'll apply t to each of our starting vectors. So x1, y1, z1. And then apply t to x2, y2, z2. When you apply t to the first order triple, you get x1, 0, 3x1. On the second vector, you get x2, 0, 3x2. And if you add your two vectors together by adding corresponding components, we should get something that looks like this. Notice that although the left side is factored and the right side is distributed, these two vectors are equal, and so that we have verified that this transformation does preserve vector addition. This is enough for us to say t preserves both scalar multiplication and vector addition. So t is a linear transformation. Okay, let's look at another example. I hope this is helping. Now we're going to consider the mapping going from vector space R3 into R2. So remember, in all these transformations, we have to be given your domain, where your vectors start, and your codomain, where you're mapping into, and we have to be given a function that tells us how to do the transformation. I'm not asked to find the image in this example. Here we're asked to show t is linear or find which property it fails. So again, I'd like to start with the operation of scalar multiplication. And I'd like to give you a moment again to work this on your own. So if you could pause the video, verify that t does preserve the operation of scalar multiplication, and after you're done, come back and we'll see how you did. I'll see you in a moment. Okay, let's see how you did. So here we're trying to verify that t of some scaled version of a vector in our domain is equal to c of t of an element in our domain. Again, we'll start with the left-hand side and grab what a typical element in your domain looks like. X, Y, Z. Again, order of operations will say simplify what's inside first by distributing that scalar C to each component of your vector. Now we'll apply our transformation, and our transformation takes an ordered triple x, y, z and turns it into an ordered pair. The first component stays the same, cx, but the second component is really a product of y and z. And if we multiply these two, we'll get cy times cz. Or if we simplify this, it'll be c squared yz, because there were two factors of c. Now the right-hand side. We'll look at c times t of a typical element in our domain. We'll apply t to that order triple. First component stays the same. Our second is the product of y and z. Now we can distribute our scalar c. So we get cx cyz. Notice that these are not equal because of the c squared versus c, so that we can say t does not preserve scalar multiplication, so t is not a linear transformation. There's no reason for us to check if t preserves vector addition, since you have to satisfy both to be a vector space. There's also no reason to always check scalar multiplication first. You could have checked vector addition as well. That one would have failed as well. And maybe that's something you should check, but you just have to check and make sure that both of them hold, or find at least one that has failed. Let's look at another example. Consider the mapping T that maps R2 into R2 defined by this function. Show that T is linear, or find a property that it fails. Now, once you do a bunch of these questions, you'll start to develop an intuition. And what you do will depend on the problem sometimes. Here, I want to jump back and look at one of the comments, one of the notes I made earlier. So if you could turn to your first page of your notes. Here I want to recognize this note I made at the bottom. A linear transformation will always associate the zero vector in your domain with the zero vector in your codomain, meaning t of 0 always has to equal 0, meaning the origin, the zero vector, does not move under a transformation. And this is the one I want to use. I want to see, does 0 get mapped to 0? Because if not, then we're done, and this is not a linear transformation. So here, let's consider the 0 vector first. Specifically, I want to check, does t of 0 equals 0? So let's start with 0, 0, an element in our domain. When we apply our transformation to 0, 0, I think we get 0 plus 2, 0, which ends up being 2, 0. This is not the 0 vector. This tells us that t does not map 0 in the domain to 0 in the codomain. T is not a linear transformation. We should probably even be able to tell graphically what does this transformation look like. So to help us with that, let's draw a coordinate system. And notice what this transformation does is it always adds 2 to whatever your x component is. So here we started at the ordered pair 0, 0, the origin, and we got translated 2 units over to the point 2, 0. So this linear transformation was a shifting of the plane 2 units to the right. Similarly, if I had picked the ordered pair 1, 1, then when you apply t to this transformation, t of 1, 1, we would have gotten 3, 1. Because this linear transformation changes our space by sliding everything 2 units to the right. So that's how this transformation is changing space. Okay, I'd like to stop here with our guided notes and move and maybe end this video. I'm going to create a second video to look at our remaining examples. I hope this is helpful, and I'll see you in the next video.